So before I start the main part of my talk, I just thought I'd ask you all to think for a moment about the problem of sending something to another planet, right? This is the night sky. This is a little later than now tonight, I suppose. And if we wind it back until we can find Mars, that's actually Mars just there, just rising over the horizon now. It's very close to the sun at the moment, so you don't get a view of it at the moment, but there it is. And when you think about it, you know, here the problem we have is you get a room full of engineers, you say, right, I want to build a spacecraft that I'm going to launch from Earth, I'm going to land it on Mars, it's going to not burn up in the Mars atmosphere when it gets there, it's not going to swing off into interstellar space and never be seen again. You know, I want all these parts to work correctly, bearing in mind that Mars and the Earth are of course both orbiting around the Sun at different rates, and so you know, it really is a tremendous problem in engineering just to get anything to Mars at all. And so, you know, one way to think about this is, so right now, the going rate for Mars, success on Mars missions is about 50%. That is, half of all the things that we've sent to Mars, either landers or orbiters, has actually got there and worked when it got there. And, you know, people look at this and they go, well, you know, that's not that great, or they laugh at things like the Mars Climate Orbiter that burns up in the atmosphere due to a small error in metric and imperial units. But in general, you know, a 50% success rate is actually a really pretty good achievement, considering just how hard this problem is. So I love this thing. This is so we got Mars over here. I think I just turned around too slowly to point out the North Polar Cap, which was visible on its way onto the screen. That you can basically, the South Pole here, North Pole up there. This is one of the big mares. I'd like to point out where the rovers are, but I actually didn't do my homework enough to be able to do it. So, but nevertheless, so what we're going to talk about tonight is essentially the two rovers that are there now and still operating on Mars, that is Spirit and Opportunity, and some of the problems and some of the technologies that went into doing them and getting them to work. And I'll look a little bit briefly at the end as to what the future possibilities might be for further Mars missions and places, I think anyway, that we should be going in terms of new missions to Mars. So the title is Mars Rovers More Than a Toy. I'm hoping, I'm sure I actually saw a number of you going and playing with the Mars Rover out there in the think tank this evening. And in many ways, actually, the experience you get playing with the little toy one there, when you try and program it to drive around and visit the rocks, is very much like what the scientists are doing on Mars every day, doing this problem. I should say the bottom down here is this is actually from the previous rover. Where has it gone? Here we go. This is Sojourner, which is the 97 rover to Mars. And just for a bit of perspective, Sojourner is about the size of, you know, a small cardboard box, whereas the other two rovers are probably the size of a table up the front here, something like that. So they're considerably bigger things. One of the amusing stories about Sojourner is that it turned out when they got it to Mars, they found that it was exactly the wrong size to send to Mars, because you can see it's just too small to kind of just drive in the gaps between the rocks, but equally it's just too big to roll right over the top of them. So when they actually got it there, they found that the places they could take it were very limited, just because of the size of rover they chose, and so that's why the Spirit and Opportunity ones are much larger. Yeah, so anyway, we'll have a series of little panoramas of Mars, taking advantage of the cool technology in here throughout the talk. Probably finish with that. So the first question, of course, is why would you bother going to Mars? And given that most of you are involved in astronomy and things like that, you probably don't need to hear this bit. But the question is, you know, you're spending an awful lot of money. It's very costly. One of these missions costs on the order of $150 million US, and that's just the cost of building the vehicle, putting it on top of a rocket and getting it there. That's not including any of your ground control, mission control costs once it's there. So why do we bother? Well, there's a bunch of arguments. The first one, and personally my favourite, is that science is worth doing regardless of the cost, right? This is finding out more about the universe. What could be more important than that? the other argument that often goes with that is that we get a lot of other benefits out of doing the science, right? Everybody knows the story about how we wouldn't have Teflon frying pans if it wasn't for the space program. It's very much true. We do get a lot of technologies out of these kinds of things that we wouldn't get otherwise. But I think in many ways, the most important one from the scientist's point of view is that Mars is the best model we have I mean, it's the only sort of alternate Earth we have that we can say, okay, Earth turned out this way, Mars, it's a fairly similar orbit, it's a small planet, but you know, it's reasonably similar to Earth, and yet it turned out entirely different. Why is that? So it's the closest model we have for a sort of second Earth that didn't turn out that way. And so it's interesting and important to study because it gives us a lot of insight into what we might expect to find further outside the solar system. And finally, and this is the one that everyone's still very excited about, is that Mars might actually have life on it, right? It's not inconceivable. It has pretty much all of the things that we think are essential for life here, just in slightly different proportions and slightly differently arranged. But it's, of all the places we know of, apart from the Earth, it's the best place to look for life. So it's a pretty good reason to go. After all, right now, our entire experience of what life is and what it means to be alive is based on exactly one example, this planet. So the big questions that the scientists are interested in asking, what forces shape Mars, right? What are the processes that drive the Martian landscape? You know, how does it change over time, and what causes that? Why isn't Mars like Earth, right? Why did it end up this dry, almost atmosphereless sort of dust ball rather than something more like Earth? Was there ever liquid water on Mars, right? Liquid water is, as far as we know, from our one example, essential for life. And so, you know, this is a very important question to ask about these things. And is there still liquid water ever on the surface or underground? You know, where would you look for liquid water on Mars, and therefore for life on Mars? Was there ever life, and is there still life? You know, obviously, probably the questions that most people are interested in hearing the answer to. So just to talk a little bit about the processes that drive Mars and how it's like and unlike the Earth, I should point out that this is really just an excuse for me to show some pretty pictures. This is the North Polar Cap. It's basically a mixture of water ice and frozen CO2. In summer it's mostly water ice, in winter obviously there's sort of snowfalls of CO2, and so you get a lot more CO2 in it. And it has this lovely swirling pattern, in fact so does the southern one, basically due to the winds moving dunes around, and so the wind patterns produce the swirls, and then the snow and ice sits on top of them. So we also get cratering as a major sort of force in terms of shaping the Martian, what we know of as Mars. This is just a nice piece of crater terrain. This next one is my favourite Martian crater, many people's favourite Martian crater. It's the smiley face crater. Particularly nice. There's volcanoes on Mars. In fact, this is Olympus Mons, which is, I believe, still the biggest volcano in the solar system. An enormous thing. This is actually the reason that this image isn't all that good is because this is from way back in the Pioneer. No, the Viking missions. Thank you. Somebody knows this stuff better than I do. There's also apparently water, or at least some sort of liquid, that flows on Mars. This is, I think it's Nergal Vallis, I'm not sure, but it certainly looks just like the kinds of desert arroyos and desert sort of flood patterns that we see in various places on the Earth. It may not be, you know, something like a sort of classic Earth canyon where there's constantly flowing water, or was at some point in the past. It may be that there's been a big flash flood that's just driven a huge amount of change very, very quickly. But you know, it's certainly evidence that there appears to be liquid water flowing on the surface at times, or some liquid anyway. And another one of that, these are the famous gullies that everyone got quite excited about 3 or 4 years ago. And here, the key is that these things, they only appear on slopes that seem to get slightly warmer than most of the rest of Mars, and they're very, very similar to the kinds of gullies we see in places like Greenland, where essentially the ground is frozen, but where it gets just warm enough for the water to start to melt, it produces these erosion gullies where, you know, a small amount of flowing water slowly produces that kind of pattern. So these are the kind of processes we see on Mars, and as I said, they're very similar to a lot of the things that we see on Earth. And so, it's an exciting place to explore and an important place to understand to see why things turned out the way they did. So then the next question is, if those are the questions we want to answer, are the rovers the right tool? Can they answer those sorts of questions? Well, we can do a lot of stuff from orbit. This is actually the Mars Climate Orbiter that didn't orbit. However, you can't see much of the details from orbit, right? For one thing, you've got a very, even with the modern Mars orbiters that have quite high resolutions, you're still looking at resolutions of maybe a metre or a couple of metres per pixel. And so any small details like these rocks here, you can't see at all. So, it's not surprising that when the Sojourner mission was launched, they had no idea what the size of the rocks were going to be when they landed. Equally, we can't answer questions like what are the rocks made of. We can certainly make some generalizations about that, right? We can measure various, we can use spectrometers to get some spectral images and determine some general things about the rocks, but we can't say what individual rocks are made of, and we can't say, we're taking sort of an average over a huge area of what the components of the rocks are. We also can't look underneath the surface of the rocks, right? Mars has a lot of dust, and certainly all these rocks have been there a very long time, and so they typically have quite a sort of weathered patina on the surface, and you like to see what's underneath and see whether there's, it's different from the dust that you've got on top. And then, of course, there's questions like how were the rocks formed, what's the soil like, are all the rocks the same? There's loads and loads of things that you just can't answer from orbit, and so naturally you want to put something on the planet, and rovers seem like a reasonable choice. I'll come back to some of the other alternatives, or another alternative at the end of the talk. So here's an example of what you can't do from orbit. The rover is in this picture, and I defy anyone to tell me where it is, but it is actually visible in this picture, and there is a huge clue for anyone who's paying attention. Does anyone want to offer me a... this one here? That's actually the lander. So well spotted for the track. The rover is actually this black spot here. So it's sitting on the edge of the crater, waiting to go and explore. That up there is the heat shield of the entry vehicle. So the heat shield landed here, the rover landed there, and it's driven along this track and then around the edge of the crater over there. But obviously, and this is the highest resolution imagery we can currently manage from orbit. So, there's a huge amount of detail that you're just never going to see. So the next thing, I have a little video, there's a cute little NASA video for the how do we actually get there. So this is looking at the challenge of actually landing the thing on Mars. So the first part of it is relatively simple, right? You stick your rover on top of a rocket, you launch it into Earth orbit, it has its own rocket engine underneath, the rocket drops various stages, and then that shoots it off to Mars. Halfway around it turns around and decelerates the other half of the way, and then the video starts. A bit of luck. There we go. Right, so this is the other part of that. So this is the landing on Mars, right? So this is the rover package. It spins off. That's the rover in that part. That was the remains of the spacecraft engine that took it to Mars. And now it enters the Martian atmosphere, and it's essentially using the atmosphere to slow down. This is an aerobraking maneuver. And so it's just skipping lightly into the atmosphere and heating up the heat shield on the front of the thing. So that was the thing you saw in the top of the previous picture. Then the parachute deploys, and again it's just sort of slowing down on its way down in. And the parachute works basically almost all the way down to ground level. So it's still decelerating here. It drops off its back shell, and then the actual rover is inside this little triangular package here, and it's surrounded by airbags, and this is where it gets a bit silly. So we're still slowing it down, the airbags are going to inflate any second, there we go. And then we get reasonably close to the surface, it slows down a little bit more with jets, and then drops the rover. And essentially we play snooker on the surface of Mars, and we see where the rover ends up, and it literally just bounces. If you look at the plans for the landing, they drew up these ellipses and said it will land somewhere inside this ellipse. And the ellipses were about 100 kilometres long and 50 kilometres wide. So, you know, you really could have ended up anywhere. And there was a lot of effort put into trying to fit the ellipses inside craters that they wanted to land one of the rovers inside, and things like that. So once it gets there, the video stops, but the airbags then deflate. The package sort of opens up, and it opens up in such a way that the rover always ends up flat at the bottom. And then the rover sort of steps up off the platform and goes out and explores. That's the theory, anyway. And one interesting thing is, so this is the same technology they used for Sojourner, the 97 one, and obviously, where is it now? Oh, it's right at the back there, never mind. So Sojourner was considerably smaller, and when they actually built these things, they didn't know whether the airbags, the airbag technology they had was actually going to be good enough to land the rovers. They thought it was about at the 90% of specification was the weight of the package they were trying to land with the Square Opportunity rovers in it. And so they essentially they didn't have any better ideas. Their attempt at a smarter lander, which was the Mars Polar lander mission, had gone spectacularly wrong 2 years before. And so they basically said, okay, we'll do the airbags again and hope that it's on the good side of 90% and not on the bad side. And fortunately, in 2 cases out of 2, it was successful. Okay, so the rovers themselves. I'm going to start by talking a little bit about the hardware, and then I'm going to talk about how we actually do things with them. So this is the basic plan of the rover. We've got a little instrument arm out front here that has various instruments, and I'll show you a close-up of that on the next slide. We've got a set of solar panels, which obviously we're looking at from underneath in this picture, that provide all of the power for the rover. So it's entirely solar powered. There's some talk of using nuclear power on future rovers, but nothing so far. There's 2 antennas talking to Earth, high gain over here and a low gain on the pole. And then there's the instrument arm, there's the camera arm, or camera, I forget what the word is now. Anyway, so we've got 2 stereo cameras over here that take your sort of big panoramas of Mars. We also have the thermal imaging spectrometer, the mini test it's called, which is one of those 2 things in the middle there. And essentially you can point that at a rock and get some sort of spectrometer reading back, although considerably less accurate than the ones that you get from the arm. On the arm itself, you've got 4 instruments. You've got an X-ray spectrometer, a microscopic imager, a Mossbauer spectrometer, and don't ask me what the difference between the X-ray and Mossbauer ones is, but I have no idea. And then a rock abrasion tool that lets you grind off the surface of the rock and look a little bit underneath. And then you have up here a couple of little workspace cameras that let you look more closely at what the arm is doing. And obviously one of the major challenges in terms of software here is you've got pictures from the main pan cameras on top of the vehicle, and you've got these other workspace cameras down here, and transferring your control from one of those to the others is actually a serious challenge, right? The pan cameras get one view of this and can tell you, one estimate of how close your tool is to the rock. Your workspace cameras give you an entirely different view, and you have to kind of make the 2 of them work together. So that's basically the instruments on board, and compared with Sojourner, this is a big improvement. Sojourner had 1 camera and one, I think it was an X-ray spectrometer, an X-ray spectrometer, but I'm not positive. But it essentially only had 1 science instrument. In fact, Sojourner was in many ways intended as a technology demonstration. Yes, we can put a rover on Mars and we can make it work and drive it around and do things with it, rather than a real science mission. These are really there to do science. They've sort of proven the technology, now they're doing science. So that's what you've got available to you, and I said what our list of grand challenges were. That's what we're aiming to solve, if that's a question. So what about the mission control? What do you do once you've got the rovers there? You've got all these science instruments, how do you decide what to do with them? And this is probably the biggest challenge of the lot. So first of all, you've got this issue of communications, right? Mars and the Earth obviously both rotate around the Sun. Mars takes approximately twice as long as the Earth does to do one orbit of the Sun. And so some of the time, the Earth and Mars are nice and close like this, at which point it takes about 3 minutes for communications to go each way, so 6 minutes round trip. Some of the time, of course, the Earth is over here and Mars is over here, and it takes, I forget what the number was now, it takes about 20 minutes each way to do communications. So clearly we're not going to be driving these things around on Mars by joystick. And Sojourner, they actually tried it at one point, and it didn't go very well, let's put it that way. They didn't try it until the very end of the mission, because they knew it wasn't going to work well, but they were so frustrated about the fact that it couldn't drive in between the rocks and go to the places they wanted, that they thought they would try and just joystick it through. And they got a lovely image back from the lander of Sojourner with one wheel hanging off the end of this rock, just about to plummet into the abyss, and decided it was maybe not such a good idea after all. Unfortunately, I can't find that image anywhere, otherwise I would have shown it today. But anyway, so you've got this communications problem. At the same time, you've got the problem that obviously Mars is rotating on its own axis, and so half the time the rover is on the wrong side of Mars to talk to Earth anyway, so you can't do any communications 50% of the time, more than 50% of the time, in fact. And the satellite dish that you need on Earth is obviously extraordinarily expensive. There aren't very many of them, there's lots of demand on them, and so even if you could communicate with Mars all the time, for example by relaying communications from a satellite in orbit, you still can't afford to pay for the telescope time. And so basically you're stuck with not talking to the rovers very often at all. And in fact, what they do is they talk to them twice a day. What they did at the beginning of the mission, it's rather less now, but at the beginning of the mission, the rover would wake up in the morning, it would get a download of commands from mission control, go ahead and execute as many of those instructions as it could over the course of its day, and then in the afternoon it would basically collect up all the data it had, do the communications with Earth, and download all of the data with the new information about where it was and what it had done, what had succeeded and what had failed out of all its commands. And then basically it would shut down for the night, and the last thing in its day's instructions would be to turn itself back on in the morning and turn on its communications so that it could get the next day's instructions. So that's basically the way they do it, and it's the only really practical way at this point. And the key here is that if something unexpected happens, the thing just stops, right? So there's no case of it making a few decisions on its own, or maybe having options that it could do this or it could do this other thing, depending on how things go. It just follows the plan one step at a time. If something goes wrong, it stops. The only additional things it does is it still does its communications and it still reports back to Earth. That's about all. So that's the sort of model you should have in your head for how we're doing the communications. And then let's look at it from the ground control's point of view, right? So, as I said, the rover, the last thing it does is it sends down its day's worth of data, and the scientists basically have 12 hours in which to figure out what to do before they have to send it up a new communication. So the scientists get together in a room and they have a big argument and discuss what the next day's science goals should be, what they want to achieve, what they've learned today that they want to react to, and so on. They produce a set of objectives that they want for that day. These are then given to the tactical activity planners, and this actually is one of the tactical activity planners with the long hair and the beard. I don't think it was as a result of Mars. He was working on the Mars mission. He already looked like that. But nevertheless, the tactical activity planners, their job is to basically sequence all of those activities that the scientists said they wanted done into the rover's day. So you've got a limited amount of time, you've got a limited amount of power, you've got to do, on the order of several hundred things over that day, where things might be, turn on a particular motor or something like that, and they're quite small tasks, some of them. But nevertheless, you've got a huge amount of stuff to do in a limited amount of power, and they have to do this in 12 hours, remember. They produce a plan, it gets past to the mission managers, and they sit around and go, okay, is this really going to work, or are we going to break our rover somewhere in here? Because obviously if you break the rover, you can't send the repair guy to fix it afterwards. So they check over that plan and make sure that they're happy that there's no mission constraints that are broken, that there's definitely going to be enough power to do the communications at the end of the day, that there's certainly going to be enough power to turn the rover on the next morning, that you're not going to drive off a cliff or any of these, any other hazardous behaviour and so on. Once they're satisfied with the plan, and that may involve going back and forth with the taps, then the final plan gets sent up to the rover the next morning. And this has to be achieved in 12 hours, and as I'm sure you're all aware, there's 2 rovers. So they're quite busy at mission control. They have an awful lot to do in the course of a day. And for the first 90 days of the mission, they did this 7 days a week, 24 hours a day. A Mars day is half an hour, I think about 20 minutes longer than an Earth day. And so they lived on Mars time, and they all got issued with little Mars watches that told you what time it was on Mars. And they were told, you will be in at work at 7 o'clock in the morning Mars time, and you will plan that, and we will upload the data at this time, and you will download the data at this time, and what you do in your 16 hours off is entirely up to you, or 12 hours off, or whatever it was. But quite frequently, this guy here, John Brezina, was a good friend of mine. And I went down to Los Angeles to visit him while he was working as a tap, and he's the only person I know who can tell you every single restaurant in Los Angeles that's open at 5 o'clock in the morning, because quite frequently he was having dinner there. So it's a really difficult process, and it's tremendously expensive as well. The estimate was they were spending about $1 million US dollars a day just on salaries for this lot and all of the other support services to get the mission done for those first 90 days. So when I said they don't do it quite like this anymore, basically they can't afford to anymore, so now they don't work weekends and they work regular Earth hours rather than Mars hours. But nevertheless, so that's the challenge from their point of view. And one of the questions is, how do the scientists figure out what they could do, right? I said they download a bunch of data and then the scientists go, oh, I want to look at that rock, or I want to dig a trench over here and look at the soil or whatever. And it turns out that they have this very fancy virtual reality tool that lets them see what's going on. This is an actual, it used to be, I couldn't find it when I looked, but you used to be able to download this tool off the internet, and you could get the panoramas and drive the rover around in the simulation yourself. But when I looked the other day, I couldn't find it anymore, so I'm not sure it's still available. But anyway, you can basically plug in, I want to go to this rock here, and I want to deploy the particular instrument, and the rover will drive over there, and the instrument will come out, and you get little virtual results back and things like that. This is the lander back here, by the way. This is Opportunity in the original crater that landed in. So every day they actually build a 3D model of the terrain from whatever data is available from the pictures that the rover has taken, and they put it into this model so that the scientists can sort of sit there in this virtual model and decide, I want to go here and do this with the rover and so on. It's really a very impressive toy. And as I say, the virtual rover responds to their commands, and they can try out different things and see how it will work out. So that's one of the tools they use. The other tool they use is a thing called MapGen, and this is something that I worked on a little bit, but not very much. And the problem here is that, as I said, those daily plans for the rover can have hundreds of commands in them. And the plans have to be produced on a strict schedule. In fact, they get about 3 hours to produce the plan for the daily activity, and it used to be done by hand. So for Sojourner, they used to have a group of people who sat there and tried to push all the pieces together and well, we have to do this for half an hour and we have to do this for 10 minutes, and how can I squeeze them all in and get them all into my day without going over my power budget and so on. And it was tremendously difficult, and one of the results was that about 70% of the time Sojourner did nothing at all. Some of the time that was because it tried to drive somewhere that it couldn't get to and it stopped because it was going to hit a rock. But a lot of it was because they simply couldn't produce a plan for a whole day's activities in the time they had available. And so what they have now is this tool MapGen, which you basically plug all of the activities you want to do in, and it automatically builds a plan for you. So there's a little piece of AI in there that's building all of these plans. But this happens all on the ground. So there's nothing smart on the rover here. All the intelligence is down here on the ground producing the plan, which then gets checked by hand and then uploaded to the rover. So there's still a way to go for the AI, but it's an improvement. And the important thing here is it produces much better plans in the sense that it uses less power, it gets more stuff done in a day, it gets about twice as much stuff in a day as the hand-built plans used to. And the Jet Propulsion Laboratory was so cautious about adopting this kind of technology that they actually had a little bake-off to decide whether they were going to use it or not. They had a room full of their best planners on one side, and they had the piece of software on the other side, and they gave them a simulated day of Martian activities and said, go and build the best plane you can. And then they compared the two plans, and then they said, okay, you guys are all fired. We're keeping the computer. It did a much better job. So a nice story if like me, you're in computer science. But anyway, it does produce much better plans, and it produces them much faster as well, which turns out to be a huge advantage, because then they can take the plans, go back to the scientists and say, hey, you know, we've actually got an extra couple of hours here. Do you want to put some more science objectives in this? We can, you know, improve the plans. So you get a much better designed activities in general. So that's the kind of technology. On board the rover, there's nothing very smart at all, as I said. It gets a straight line plan, and it just executes it. And this is what Sojourner did, and the estimate is that over the course of its 90-day, or just a little less than 90-day lifetime, Sojourner moved about 500 metres, which is, I think, slightly slower than a snail. So just for perspective, it's not really very impressive. The key is that if something went wrong, as I said before, Sojourner just stopped and waited for instructions, and this happened a lot, right? It was they found it very hard to tell it, you know, just drive over there without it meeting any obstacles that would stop it. And so it would literally take them days to do a single science observation with Sojourner. And they were very keen to do something about this with Spirit of Opportunity, and they've certainly succeeded to some extent. Opportunity has now travelled 8.6 kilometres total. Spirit's travelled 6 and a bit, I think. So, but you know, this has a lot to do with how much science you're doing and how many other things you're doing. It's not just how much of Mars can I drive across in the time available. One of the important things is the new rovers can do some navigation around obstacles on their own. So they do actually have enough intelligence on board that they can go, oh, there's a rock there, let's try and find a path around it and carry on and still execute their original plan. So that's a big improvement, but it's still not much of an improvement. It actually takes 3 days for them to do a microscopic image of a rock. So if you have the rover sitting somewhere and the scientist goes, I want a picture of that rock over there, it takes 1 day to drive fairly close to the rock. It spends the second day doing the sort of fine manoeuvring to get close enough to place the instrument. The third day it actually puts the arm out and places the thing on the rock and takes the measurement. And that's standard. It never takes less than that. It's always 3 days per piece of science. Right? Obviously, if you do lots more experiments at a single rock, you can do those faster. But in terms of the driving up and so on, it takes 3 days each time. And that's one of the reasons why the rovers are so expensive, right? Because you can't just go away for the weekend and say, just drive up to that rock, because it can't do it. Every day, they need to look at where the rover ended up and decide what to do, you know, how to achieve what their goal was from where they ended up today. There's not much smarts on board at all in terms of that kind of thing. So one of the good examples is Opportunity. Actually, if I can, I've lost my remote control, but anyway, I just can't see anything without it. If I change the system, right, this is Opportunity on its lander, sitting in the crater where it arrived, and right, this over here is that big sort of rocky area that they first saw when they got the first images back from Opportunity, and that made all the scientists very, very excited. And one of the things they wanted to do was they wanted to go up to some of these rocks, but you can see that the crater wall sort of slopes up, and these are halfway up the crater wall. And so they got Opportunity off the lander, they did a few other things, and then they decided to drive up to one of the rocks. I think it's actually one of this set here. And drove the lander, and they got it about 1 metre away from the rock that they wanted. Then that was sort of what they'd achieved that day. They looked at the situation and they said, okay, we've got a problem. The wheels are slipping because of the slope that we're going up, and that rock's about 1 metre away. So there's so little intelligence on board the rover that rather than saying, just keep driving forward until you get to the rock, which, you know, naturally is what we kind of want to do, they had to actually command it, drive forward 1.5 meters, and just hope that there would be the right amount of wheel slip that they would end up in the place they actually wanted to get to, about a metre forward by the end of the next day. Unfortunately, it worked out fine and they got good images of the rock, but that was the kind of thing that they were trying to do, and the way they have to go about finding this thing. So, can I have my slides back? Thank you. Right, so what have they achieved? I'm not going to try and summarise everything because obviously they've been there for 2 years each, and that's obviously a lot. This is the first thing they've achieved is they've explored more of the surface of Mars than ever before by a huge margin, right? So this is the Spirit traverse, I think. Yeah, this is Spirit. It started off here. That was the crater that you saw next to back at the beginning of the talk. It's now driven all the way over here to the Columbia Hills, as they call them, and done a bunch of stuff there. And it's now sitting down here, and it's basically it's winter now for Spirit in the southern hemisphere. So it's trying to find a nice north-facing slope so that it maximises the amount of sun it gets on its solar lines. And so it's basically going to sit here on the side of the hill for quite some time and do very little because there's so much reduction in available power in the winter because the sun is close to the horizon that there's not much it can achieve. So that's basically what Spirit has done. This is Opportunity's path, and there again, this is where it started at Eagle Crater, drove out and investigated Endurance. Much to everyone's surprise, they managed to get it back out of Endurance Crater and they're now heading down here to this very large Victoria Crater, which they seem quite excited about, but to be honest, I can't imagine how they're going to get it in that one. But again, as I said, this is about 8.6 kilometres, the total trail there, so they've really explored a huge amount of Mars. It's very impressive from that point of view. The biggest achievement, sort of the big headlines, they really do have pretty much definitive proof that there was once liquid water on Mars, which is, you know, obviously it's been hypothesised from images from orbit before, but it's a big deal. And the sort of set of pictures of proof that they offer, these spherules in Earth rocks, we typically see them in places where they've been deposited by water running across the rock. And these cracks, or vugs as they're called, are again indicative of places where basically there's been some water-soluble salt crystal deposited there, some long thin crystal presumably, and then as water has subsequently flowed across the surface of the rock, it's dissolved that crystal and left the hole sort of in the shape of the crystal that would have been there. So that's two strong arguments for water. The third argument is there's a lot of rocks like this with very fine stratification of them, and in fact this one's a particularly good example, though the picture is a bit terrible, of one that has rippled layers in it that look very much like it was formed in sort of flowing water depositing layers of sand. Very similar to things we see in those sorts of rocks on Earth. And finally, they've found plenty of evidence of this iron compound jarosite. And jarosite on Earth is only formed in situations where essentially there's slight sulfuric acid in groundwater, and it deposits the iron minerals, dissolved iron then gets deposited in the form of this jarosite, and this is really quite a strong signal from one of the rocks that Spirit found. So they've got a lot of evidence now that there definitely has been liquid water flowing on the surface of Mars in the past. So that's one of the major achievements, or probably the most major achievement. In addition, they've greatly increased our knowledge of Martian geology in a whole bunch of other ways. They've, for example, they've analysed what's going on around the different landing sites. Spirit's landing site appears to be a very old lava flow that's since been heavily cratered. And Opportunity's landing site is apparently the shoreline, or close to the shoreline of a salty lake. And so that's why you get very distinctively different. I'll show some more pictures in a minute. You can really see the difference between the two kinds of terrain. The Martian atmosphere, they've also made some very important measurements of. I mean, firstly, they've been able to do some sort of measurements of various gases and so on. They've studied the dust that's in the atmosphere. One of the instruments I forgot to mention is they have a bunch of magnets on the top of the rovers, and it turns out that the dust is highly magnetic. And so they've collected all the magnets and been able to study it that way. They've also managed to take pictures of passing dust devils, and in fact, Spirit was fortunate enough at one point to have one pass right over the rover and blow all the dust that had accumulated on its solar panels away. And suddenly they got this new burst of power and sort of running around trying to explain how this could happen. And they've obviously produced many other important discoveries about the geology of Mars. Sadly, the one thing they haven't managed to do is to discover life on Mars, which obviously would really be the perfect discovery. Largely, I think most people suspect that's because they took the wrong set of instruments. So if you talk to the Martian scientists, I would guess the majority of them believe that there is or has been in the past life on Mars. They might not say it in public announcements, but certainly the impression I have from people I've talked to, that many of them believe that. But so far, in fact, unfortunately, the best instrument sent to Mars for detecting life there was one of the ones on the Beagle, and obviously that wasn't a huge success. It falls into the other 50% of Martian missions, unfortunately. But at least, you know, they've discovered lots of the things that we think are required for life. We now have pretty much, you know, certain evidence that they exist or have existed in the past on Mars, and so the discovering life will certainly be a major feature of future missions. And oh yes, I thought I'd finish with a few more pictures. So one of the things they've done that's really quite surprising and has changed NASA's plans in a number of ways is they've shown us a whole new Mars. So this is Viking Mars. That's the Viking lander there. And you can see it's basically a rocky, dusty plain, scatterings of rocks. It looks very much like Mars has been basically pounded by meteorites, and these are the little bits of rock that have been spat out in the cratering. This is Sojourner's Mars, and you can see it looks basically the same. Dusty, rocky plain, bunch of large rocks, but nothing that looks like bedrock or anything like that. This is Spirit's Mars, and again, you know, pretty much dusty, rocky plain. But the really exciting one is, of course, Opportunity's Mars, and Opportunity's Mars looks nothing like the rest of these things. So here, as I said, it's probably the edge of a salty lake, or a salty lake, I'm sorry. But also, really importantly, this is the actual bedrock. It's not just a layer of broken rock from repeated meteorite strikes sitting on top of the original bedrock. We actually get to look at what the rocks at this point on Mars look like here, which is, you know, definitely a new first for these rovers. And one of the consequences of this is that before the rovers arrived, the next mission planned for Mars was planned to be an even larger rover, and the intention was to put a huge number of science instruments on a single, very, very capable rover, drop it on Mars and just go and explore. And NASA has actually changed its mind about that. And the reason it's changed its mind about that is because up until these two arrived, they thought they knew what Mars was like, and they thought it was that dusty, rocky plain that 3 out of 4 Mars missions has seen. And in fact, they're now opting for the next rover mission to be very much like this one, but with slightly different instruments on board. But again, 2 rovers. And the main reason for that is because they don't want to end up seeing only one of these types of domain with their terrain with their new, more capable rovers. And so it's very much changed their viewpoint of how to go about the future exploration of Mars, knowing that there's different kinds of Martian terrain that they've never seen. Okay, so moving on to the future. This is only a couple more slides. So this is me, by the way, and this is the prototype of future rovers that we had at NASA Ames when I was working there. And basically the stuff that we were working on was solving some of the hardest parts of the current way that Mars missions are done. Right? One of them is the fact that it takes 3 days just to take one picture of a rock. You'd certainly like to be able to tell the rover, go up to that rock and take a picture, and have it come back when it was finished and say, okay, I did that. What would you like me to do next? Rather than having to command it each day explicitly, now move 6 inches forward and deploy your arm and so on. Sorry, that should be 15 centimeters forward. Right, so that's a big problem. The second thing is that ground control is enormously expensive, right? And you just cannot do many Mars missions. You certainly can't send more than 2 rovers if it's going to cost you $1 million US a day to do your ground control. And so the stuff that we were looking at, and that's certainly a big part of NASA's future investment in rovers, is how to make them smarter and how to put more of that intelligence on Mars rather than on Earth. So one of the things is the ability to change their plans when things don't go as expected, right? To have plans with branches in them that say, okay, if you've got enough power left, go ahead and do this thing, but if you're short on power, just do this other thing instead. You know, do something worthwhile with that extra resources that you have. Also to reduce the amount of time that you need to communicate, right? One of the big problems is having to talk every day to ground control. If you could only talk once a week, great. If you could leave the rover on Mars for months at a time and have it just phone home every so often and say, hey, I've just found a whole big pile of dinosaur bones. Do you want to see pictures of these? That would be fantastic, you know? Then we could afford to put 20 or 30 rovers on Mars and really explore the planet, just by having more smarts on the rover and the ability to go, hey, this is interesting, whatever interesting means, and I'm going to tell you about this. This stuff is all routine. It's stuff that I've all seen before. I'm just going to keep driving to whatever my destination was. And in fact, the dinosaur bones one is a good example of one of the things that the current mission planners are terrified of. They're really worried that they might just drive past something at the moment. They might say, I'll go drive, 50 meters over that ridge and over there, and over the other side of the ridge there'd be a Martian city or a pile of dinosaur bones, and the rover would drive right on by and wouldn't even take a picture of it. And right now that's what would happen, except that they only drove a very short distance every day. But if you could put a little more intelligence on the rover, and that's what we're working on, then that's, that sort of thing isn't a problem anymore. Okay, so some other things that are important. One of them is sample return, and this is something NASA is planning, although, when I started at NASA in 2000, it was planned for 2009, and a couple of years later it was planned for 2011. And I think now 2015 is about the earliest you'll hear it, so it could be a while. But Mars sample return, obviously a really interesting mission, right? If we could have some of those rocks and soil samples and things back here on Earth to study, that would really be fascinating. Huge advances in what we could do. The geologists estimate that in one day, the current Mars rovers are capable of doing what sort of your field geologist student could do in about 45 seconds. And so having one of those rocks here that your geologist could study, there's just so much more capability for science if you could do that. Drilling is another huge thing. As I said, we're really interested in the life question. Life is generally associated with liquid water. Where is there liquid water on Mars? Well, the recent orbiter missions have shown us that it's underground, and there's almost certainly liquid water at depths ranging from 1 to 10 kilometers underground. So one obvious kind of mission that you would like to do is to do drilling missions. Stick something on the surface, drill down, find the liquid water, see what it's like, see whether there's life in it. Certainly there are plenty of examples now being found of life on Earth over a kilometre underground. There's lots of recent discoveries of life that's basically surviving on the oxidisation of minerals in the rock well below the surface of the Earth. And so it's a good place to look for life on Mars as well. And finally, the poles are obviously really interesting. That's the other place on Mars where there's easily accessible water. Admittedly, it's frozen most of the year, but it's certainly likely that in summer it could get warm enough in certain spots that there could be some liquid water there. And so that would be another obvious place to go and look. Unfortunately, as I mentioned before, Mars Polar Explorer was another of NASA's somewhat spectacular recent failures on Mars missions. So, right, I think that's about it. Oh, right, I said I'd come back to this. I almost forgot I had this slide in here. So the question is, are rovers the best tool? And I sort of said, well, you can't do everything from orbit, but I left out the other obvious solution, which is to send people. Unfortunately, my claim, anyway, is that for the money, rovers are still the best tools. Now, I did say, the rovers do in one day what competent field geologists could do in 45 seconds, but you get an awful lot of 45 seconds for your money, and that's the real key, right? For the cost of a crewed mission to Mars, you could probably send 100 or more rovers, right? By the the time you think about the amount of the amount of mass you have to send, right? Because you have to send some number of astronauts. You also have to send enough food and enough supplies to get them there and get them back. And the trip there is going to be 6 months. The trip back, if you stay for a short time, is going to be much, much longer. It's probably going to be 18 months. So you're looking at 2 years in space, or else you're looking at 6 months there, 6 months back, but about 18 months on Mars. So you're looking at slightly more than 2 years in terms of supplies and so on. So doing a manned mission is tremendously challenging. There's a very good book by a man called Bob Zubrin called The Case for Mars, where he looks at sort of the minimum cost kinds of missions that you could do that let you spend enough time on Mars to actually do something other than plant a flag and take a few pictures of footprints. And I thoroughly recommend it. But nevertheless, robotic exploration is far more cost effective. In the long run, you can certainly do a lot more, right? You get so many more 45 seconds worth of field geologist time that you end up winning in the end. And as the capabilities of the robots and the intelligence on board gets larger, gets greater, that advantage will only improve. So my final point is there's no point in going ourselves unless we plan to stay, right? If what your intention is to establish a human colony or a base on Mars semi-permanently, then by all means, I think it's a fine thing to do. But if all your intention is to plant a flag and put some footprints on Mars, then send the rovers instead. It's a much better use of your time and money. So that's the end. This is the rover waving goodbye. It's not supposed to do that, by the way. The suspension system is designed so that all 6 wheels remain on the ground at all times. Oh right, I wanted to go through the last of these cool pictures before I finish. Thanks very much for your attention. I'm happy to take questions either in here or outside afterwards. Shall we show the cool tricks with the... Alright, let's see if I can... Let's back to the beginning. Oh, that was the first one, was it? Sorry. Right, so this one's the one you saw for most of the talk. This is the Mars Pathfinder picture with Sojourner over there. This one is... this is actually where Opportunity is right now. So this is its current view out, and I just think it's a brilliant picture, right? So you can see some solar panels over here. There's some more solar panels over in the corner there. Here, right, so there's some solar panels, and then there's some more over here, and you should be able to see. The thing I can't see in this picture anywhere is the tracks for how it got here, but there must be some. Oh, they're behind it. Yes. Oh yeah, so you can see a few tracks here, and presumably they go off over there somewhere. But yeah, so this is where Opportunity is right now, and it's as I showed you on the map, it's heading up onto the rim of one of the really large craters. I think this is I believe this is Beagle Crater that we're in right now, which is a much smaller crater, very close to Victoria, which is the one that its current goal is. So the next one, this is, as I said before, this is the view from the lander. This is sort of the first morning for Opportunity, when they woke up and the thing landed. The first image it sent back looked like this, and you can imagine how excited the scientists were when they saw real bedrock, a completely different terrain with none of the rocks scattered everywhere and so on. In fact, they were very worried because they had no idea what this stuff was. They were quite concerned that if they drove the rover off the lander, it might just sink into the ground. They had no idea how soft or hard this thing was. One of the nice things is you can just see over there, and there should be another set visible somewhere. Oh, there's some over here. So these sort of marks on the ground around here are from the airbags when they are deflated, and this series of little circular marks up here is from the rover bouncing into the crater. So those are actual bounce marks where it landed on its way into the crater. And then this one is sitting on the rim of the crater, looking back down. Unfortunately, the interesting stuff is all over your right shoulder. Oh, but possibly if the wonders of modern technology, you can move it around. Or, okay, we'll try and bring it back around to the front. But you can see the lander. Unlike Sojourner, there's no camera on the lander, which is why you never see pictures of the rovers from the third person perspective. So all the pictures you get are from the rover themselves, but that's the crater that it landed in. There's that rocky outcrop again, the lander. And then you can see basically what it did. It came off the lander, it explored the soil around here. Swiftly move around. Don't you just want one of these at home? I really want one of these at home. Right, here we go. Yeah, so there's the lander, there's that rocky outcrop that it saw. It came off the lander, did some measurements on the soil, headed up in this area. That was where it was playing around with the first measurements of the rocks. That's where those pictures of the spherules and things, the first real evidence for water was found. And then this is attempting to come out of the crater over here, and they actually failed and had to come back and come obliquely out of the crater over this way. I don't know what it's done there. I assume it's just turned around and gone back from the crater or something. But yeah, it's about to head off. Can we see the heat shield? The next thing it went to was to investigate the heat shield, but you can't quite see it in this one. Anyway, is that the last one? Oh no, this is a spirit one. Right, this is, I think this is where spirit currently is. I think this is the last one. And again, this is on this hill that it's trying to sit on for the remainder of the winter to conserve its power supplies. And again, you can see the series of tracks that it used to get up here. So it came over that ridge, drove across here, a little turn there, and then it's come up to here. So yeah, I think that's the last one. Is that the last one? That is the last one. Right. So thanks very much, and I hope you enjoyed the talk. I'm happy to take questions if anyone has questions.
What would it take to say definitively that there was life on Mars?
Oh, it's a good question. I think little green men wandering around on video would probably help a lot. It's difficult to know. It depends a lot on what kind of life it is, right? So if we assume that it's something carbon-based that looks a lot like the sorts of things we see here, that's built of the same molecules, then certainly there are things you could build to detect that kind of life. Right, so there are instruments that, for example, DNA fluoresces under certain wavelengths of light, so you could do things like that to detect it. But it's certainly a difficult challenge, particularly if you think about different kinds of, potentially not DNA-based life based on different molecules. Then it's certainly a very, very difficult question to answer.
Are there efforts being made to make the communications faster between here and Mars?
That's the speed of light. So there's nothing we can do about that. There is talk about putting a series of satellites, enough satellites around that you could have communications with the planet at all times. In fact, I think the satellites on Mars now all have Ethernet addresses, so in theory the net already extends to Mars. But yeah, so there's some talk of establishing something like a ring of communication satellites. But you still nevertheless have the problem that it's at best 6 minutes round trip just for the speed of light. So. Sorry?
Why are they so slow?
The rovers. Mostly because they're not very smart, right? So you can't tell them drive off over that ridge and go and do something because they're not smart enough to not get themselves into a lot of trouble. And so they just drive them very, very slowly. Just because, the thing is you spent, $250 million US getting that thing to Mars. You don't want to wreck it once you get there, right? You want to be able to say 2 years later, hey, they're still going, and apart from one wheel that doesn't turn anymore, things are still running fine on our 2 rovers on Mars. And as soon as you start driving them fast, you're just taking more risks. So, yeah.
Can I understand the communications more clearly? Are all communications direct to the rovers, or is the capacity in orbit?
Oh, that's a good question. Almost all the major communications are direct to the rovers, but they do They do have the capacity to communicate with the orbiters. So there has been some stuff where they've done.
I was thinking about your massive data downloads. You could stage it, couldn't you? So
You could, yes.
Leave all the data.
The problem in general is that basically what you want to do on Mars is you want to have a really small transmitter and a really big receiver,
Yes.
right? Because you don't want much power drain on the rover. And so in order to communicate with orbit, it's a lot closer than it is direct to Earth, but the size of the receiver on the orbiting spacecraft is limited. And so I'm not sure how the trade-off plays out for all possible rover designs, but it's certainly, I mean, it's one of those things where you say, okay, if I do it via orbit, then this is the bandwidth that I can manage because of the power available on orbit and on the ground. If I do it direct to Earth, I get to use the biggest radio telescope I can find here, and so often that trade-off works out better to do direct communications to Earth. Yeah.
When we're looking at pictures like this, how much colour correction is done so it looks like what we can recognise it on?
In general, not too much. So you should be reasonably confident that this is actually what, if you were standing on Mars, what it would look like. I mean, probably 90% of the pictures they don't send colour at all, because you have to send 3 times as much data. But the ones that they do, they're reasonably confident. I mean, there are certainly plenty of false colour images out there as well, but the ones that I've shown you today are generally as close to uncorrected as we can manage. You had a question?
Well, how do they know exactly how much power the rover has at a certain point? So it takes a certain amount of time that way to get back to the person, well, that some of the power might be gone.
Right, that's a good question. So essentially what they do is they have a pretty good estimate for how much their solar panels will gain, right, from just sitting there in the sun. And they're just very, very careful about it, right? They don't get close to the thing. So I had a picture of one of the plans, and it had the little tower thing at the bottom. And they basically map out exactly how much power they expect to have if things work out, normally. And then they don't let it get